If you could take your seats, ladies and gentlemen, we'll begin promptly. Well, if you're going to be quiet, we will start a minute early. Good evening, ladies and gentlemen. My name is Rob Gell. I'll be your Master of Ceremonies and moderator for this evening. I've been asked to take those roles by the Australian Meteorological and Oceanographic Society, or AMOS, which is the organisation that has facilitated this meeting. AMOS is a professional society representing atmosphere and ocean scientists in Australia, and AMOS counts Australia's most distinguished climate scientists amongst its members. We wish to acknowledge our co-hosts in the planning and promotion of this event, Monash Sustainability Institute at Monash University, in particular Tal Keston, the Global Cities Research Institute at RMIT University, in particular Frank Yardley and Jane Mallett for their help in securing tonight's venue, the Australian Research Council Centre of Excellence for Climate System Science, the Melbourne Sustainable Society Institute at the University of Melbourne, the Centre for Sustainable Regional Communities at Trobe University and Victoria University. Thank you all for your great assistance in putting tonight together. We have a full house, ladies and gentlemen, for your information, and a waiting list of 200 to come along to listen to esteemed scientists tonight. And I notice, just as an observation, a number of esteemed people in our audience as well. There are already, I've seen 2 or 3 former Victorian parliamentarians. We have current parliamentarians with us as well, and a number of notable academics are part of our audience this evening. The objective of this evening's event is to make our top climate scientists available to the public to explain the Intergovernmental Panel on Climate Change's latest assessment report. It won't be a policy discussion or debate about policy. We're talking tonight about the science. There will be an opportunity for you to ask questions towards the end of the event, and you can still submit your questions. We already have a number via Twitter using the hashtag AskAMOS. And I don't know whether that's on the screen or not, but I can repeat it for you if you wish. AskAMOS. You should note that the event is being visually recorded. If you don't want to be part of that record, you probably should move towards the back of the room. Now to begin. The 5th assessment report of the Intergovernmental Panel on Climate Change was released last Friday. It's a comprehensive assessment of the latest climate change science from the world's foremost experts on climate change. The IPCC was formed in 1988 to provide the world with a clear scientific view on knowledge on climate change. It now provides regular assessment reports that review, synthesise and assess the latest research and information available to us on climate change. Each series of reports takes about 5 years to prepare and involves hundreds of expert authors and reviewers and an exhaustive process of drafts and reviews. And I'm sure Scott Power, who will be addressing us shortly, will provide testament to that. The report recently released is the 5th assessment report, known as AR5. Now, these reports are used as the definitive reference on climate change, science used by governments, business, academics, and many others across the world. IPCC assessment reports are divided into 3 parts, prepared simultaneously by 3 separate working groups, then released independently. The first group, which released its contribution last week, describes the physical science basis of climate change. The 2 other groups will release their reports next year. Working Group 2 will be on impacts, adaptation and vulnerability. It'll be released in March. And Working Group 3 will produce their report in April next year on the mitigation of climate change. And I'd like to introduce Dr. Scott Power from the Australian Bureau of Meteorology to really set the scene and provide us with some insights into climate science and what the AR5 report is about. Scott is the Senior Principal Research Scientist at the Centre for Australian Weather and Climate Research at the Bureau. Scott is a coordinating lead author of Chapter 11 of the report, Near-Term Climate Change Projections and Predictability. Scott is also a co-editor of IPCC Working Group 1 Annex, Atlas of Global and Regional Climate Projections. He's a member of the core writing team for Working Group 1-3 Synthesis Report as well. His primary research focuses on climate variability and climate change in and around the Pacific Ocean. And he's now given us an overview now of the key new findings discussed in the report. Please welcome Scott.
Thank you very much, Rob. Before I start, I'd also like to thank the sponsoring agencies, AMOS as well, RMIT, Monash and the other universities. And I'd also like to thank Andrew and Tal and Ailey for organising the event. Today I'd like to use the latest IPCC report to talk about climate on Earth, and in particular 4 questions. First of all, how has climate changed in the past? What caused the changes that have been evident? What will happen to climate in the future? And to what extent will humans influence future climate? I should say it's a fantastic turn-up. It's great to see so many people interested in science, although I suppose really you might start becoming here to throw rotten fruit at us. But if you are here to throw fruit, please wait for the other panellists to come up on the stage. So let's begin by examining the past. The very first thing I wanted to show you was a record of atmospheric carbon dioxide concentration. And this is for the pre-industrial period, before the Industrial Revolution began. And it shows an enormous amount of naturally occurring variability all the way back 800,000 years ago. So this is so it starts off at 800,000 years ago through to just before the Industrial Revolution. And you can see that just through natural processes alone, the concentration of CO2 in the atmosphere vacillated between values of something like 200 parts per million up to about 280 parts per million. How do we know this? We know it through some very clever, impressive science where people, scientists and others, visit Antarctica and Greenland. They drill deep ice cores and then they analyse what's in the air bubbles trapped inside those long ice cores. And so we're left with magnificent records like the one you see before you. So what's been happening since the Industrial Revolution began? So this is on a different timescale, a very, very different timescale, from 1750 on the left through to 2010 only on the right. There's been further increases since then. You can see that it started off around about 280 parts per million, and now it's exceeding 380, and now it's moved on close to 400 parts per million in recent times. So how do we actually compare these two plots? This one, which extends for approximately 260 years, and the previous slide, which extended over a period of 800,000 years. Well, in order to make that comparison, you have to squeeze this plot up a little bit, actually quite a lot. And in fact, you can't squeeze it up enough. But if you get a clearer idea of what's actually happened. So there was this meandering or this vacillation prior to the Industrial Revolution, and then once the Industrial Revolution began, the concentration of carbon dioxide, CO2 in the atmosphere spiked up. And the really impressive thing from this plot is that the values that we have now are higher than have been experienced for at least 800,000 years. And of course, Homo sapiens haven't been on the planet that long. And so that means that the CO2 concentrations we currently have are higher than have been experienced by Homo sapiens that have come before us. And if that must be one of the most important scientific facts that's ever been uncovered. So that's carbon dioxide. And at the same time, in more recent times, we've also seen an increase in global average temperature, global average surface temperature. This shows at the top, it shows a time series of global average temperature anomalies from 1850 through to near present. And in everyday language, anomalies sometimes mean, oh, something weird's going on. In this context, we mean it to be the difference between the global average temperature and a reference value. And in this case, the reference value is the average global mean surface temperature over the period 1961 to 1990. So values below that grey dashed line indicate that the temperature of the Earth at the surface was lower than that average, and values above that grey line indicate that the temperature of the Earth was above the reference value. And so you can see that there's been lots and lots of year-to-year changes, decade-to-decade changes, but there's been an increase to higher temperatures in the last 50 years or so. The plot underneath shows something very similar. It's decadal average temperatures of exactly the same variable. And you can see that, again, there's lots of vacillations, a lot of that due to natural processes. There's also been an increase in temperature, in the decadal average temperatures over the last 30 years. And in fact, the first decade of the 21st century is the highest decadal temperature in the instrumental record. Now, what's causing all of these bumps and wiggles in the time series? Some of that is due to volcanic eruptions that modify the climate system and lead to a temporary cooling of the planet. Some of it's due to what climate scientists refer to as naturally occurring internal variability. So this internal variability includes things like the El Nino Southern Oscillation, which includes El Nino and La Nina. If you get an El Nino, that can lead to a short-term warming of the planet. If you get a La Nina, it can lead to a short-term cooling of the planet. And there are internal processes, something like the Interdecadal Pacific Oscillation, for example, that can lead to these transient warmings and transient coolings in the climate system. Now, we've so far looked at CO2, carbon dioxide, we've also looked at globally average surface temperature. What else has changed in the climate system? This plot provides a quick summary of other things that have changed in the climate system. So begin from the top left, you can see that sea ice in the Arctic has diminished in its extent. Water vapour averaged over the whole world has increased. Air temperature, not just at the surface but at the lower few kilometres in the troposphere, have increased. The glacial volume averaged over the whole world has decreased. Temperatures over land have increased. Snow cover has tended to reduce. Sea level has increased. And the amount of heat contained in the ocean has actually increased. And the temperatures in the air over the ocean have increased. And the sea surface temperature itself has also increased. So all of these changes are consistent with the idea that the planet is warming up. So on the one hand, we have these increases in carbon dioxide, and on the other hand, we have all of these indicators of a warming planet. Why is it that scientists put these two things together? Well, that connection comes through the greenhouse effect. And there are many experts in the audience, but let me just very briefly go through the basics of the greenhouse effect. So we have radiation coming from the sun through the atmosphere, and then it hits the surface of the Earth, and the surface of the Earth warms up. And as the surface of the Earth warms up, it gives off long wave radiation. And a lot of that long wave radiation passes through the atmosphere and goes back out to outer space, cooling the planet off. But because the atmosphere contains so-called greenhouse gases, some of that long wave radiation is absorbed by these greenhouse gases in the atmosphere. The atmosphere then itself warms up, and as it warms up, it too gives off long wave radiation. Some of that long wave radiation will go to outer space, but some of it will come back down to the surface of the Earth. And so the surface of the Earth is receiving a double whammy, if you like. It's receiving the radiation directly from the sun, and it's receiving this long wave radiation from the atmosphere. And so what we've been doing, what humans have been doing through burning of fossil fuels, through land use change, for example, is increasing the concentrations of these greenhouse gases. So what that does is it strengthens that second whammy. And so as a consequence, the planet warms up. Now, in order to determine the magnitude of that warming, it's not something you can do on the back of an envelope. You can try to do it on the back of an envelope, you're probably not going to be too successful. So you really need to take into a whole host of different processes. You need to take into account that there's a huge ocean out there. You need to take into account that we've got clouds. There could be wind changes. There could be a reduction in sea ice or an increase in evaporation, for example. All of these things play a role in ultimately determining what the response of the planet will be to increases in greenhouse gases that are being caused by human activities. And we're very, very fortunate to have, based on developments and advances in mathematics, in science and in technology, over hundreds of years, literally, that enable us to simulate the climate system. So these climate models, or Earth system simulators or models, encapsulate much of the physics of the climate system in mathematical form. And so they allow us to do a number of things. One of the things they allow us to do is to improve our understanding of what's caused the changes we've witnessed in the climate system. So here's just one snippet of the sort of things you can do with these climate models. This shows a time series from 1860 through to near present of globally averaged temperature from 3 different sources. The black line you've already seen, that's the observed temperature record. with the warming towards the end and lots of bumps and wiggles in between. And then there are two coloured, a red line and a blue line. These are the results taken from many, many models, both the most recent generation of models and the second most recent generation of models. And you can see that these models have been forced in a very special way. So in these models, we only include the influence of natural processes. So we include the influence of volcanic eruptions, and we include the influence of solar variability. We don't include the influence of increases in greenhouse gases. And so if you do that, you can see that the degree to which the models are able to simulate the observed record is deficient. That's if you only include natural processes. And by the way, the yellow traces are from individual models. Each individual model will have its own internal variability. With these sorts of simulations and with projections, which we'll come to later, we don't try to predict the phasing of individual, naturally occurring, internally driven changes to the climate system. So for example, in the real world, in a particular year, let's say 82, 83, the world has experienced one of the largest El Niños on record. Whereas in the models, some of them will have El Niños, some of them will have La Niñas, and some of them will be in a neutral state. So that's one part of the equation which we're not trying to replicate. So we don't, as climate scientists, to expect to replicate year to year and even some of the decadal changes that depend upon this internal naturally occurring variability. But what happens now if we include, in addition to the natural processes, greenhouse gas increases and increases in other greenhouse gases, carbon dioxide increases and other greenhouse gases, as well as other radiatively active aerosols? You can see that all of a sudden the models do much, much better at replicating what's actually been observed. And one of the important things it does is to replicate the accelerated warming that we've seen over the last 50 years or so. But again, you'll notice that collectively the models don't capture these year-to-year fluctuations, and we don't expect them to. But you'll notice that within the cloud of uncertainty, reflected by the yellow lines, for example, the observed pattern tends to fit within that range of possibilities. So that what this illustrates is that the models are replicating changes due to these externally forced processes like volcanoes, solar variability, greenhouse gases, but they're not replicating the exact timing of the internal processes like El Nino, La Nina. So that's the history from over 800,000 years to present. But let's now focus more on what's been happening over the last 10, 15 years, primarily because this has been receiving an enormous amount of attention in the media. And some people have been referring to the feature here that you can see at the end of the plot, where the observed temperature is below the model mean. Some models capture it, some don't. The model mean is above the observed. So what might be going on there? Well, some people have been referring to this as a hiatus. However, it's important to note that it's a hiatus in one particular statistic, whereas for many of the features of the climate system, there hasn't been any hiatus at all. So for example, the world has continued to be anomalously warm. So the temperature of the world didn't drop back down to pre-industrial values. It's still at near record values. Second, as I pointed out before, the first decade of the 21st century is the warmest decade in the instrumental record. Third, as I mentioned previously, each of the last 3 decades has been warmer than the preceding decade. And furthermore, sea level has also risen over this same period, trended upwards. And as has deep ocean heat content, the amount of heat in the deep ocean. And finally, one other thing which is a bit closer to home is that we've just seen in the last few days Australia reset its record for 12 consecutive months. And the new record is very, very substantial compared with the old record. So you might ask, on the basis of all of this information, what hiatus is it that people are talking about? Well, specifically what they're talking about is the trend in one particular thing, which is global mean surface temperature over the period 1998 to 2012. And you can see that that trend is lower than the trend over a longer period. Why might that be the case? Well, this is something that the authors of the IPCC looked at very carefully. Before we do that, it's also important to note that there are other periods when we had 15-year trends that didn't represent the trends over much longer periods. So it's a little bit of it can be a misleading thing to look at a trend over such a short period. Nevertheless, it's an interesting question, and so the IPCC report addresses it, and it concludes that this relatively slow trend in global mean surface temperature is due to a combination of factors. If you like, it's a little bit of a perfect storm of three different elements. One is associated with this internal variability. It turned out that from internal processes alone, there's been a cooling that's helped to offset the warming that would have occurred from anthropogenic forcing. A second factor is that as part of that internal variability, some of the heat has moved from the surface, where it would have heated the atmosphere, through to the deep ocean. And also there's been a cooling trend in association with changes in volcanic activity. And similarly, there's also been a cooling trend over that 15-year period associated with a reduction in the amount of radiation the Earth receives from the sun. So you put all of these things together and it tends to try and offset, not completely successfully, but offset the warming that would have occurred had the anthropogenic forcing shone through. So that's the recent past. The other point that should be made when you look at this plot is how using recent trends is a very poor guide to projecting what might happen next. And you can see, for example, if you use look at these couplets. So if you used the trend in one of the blue circles to predict what was going to happen to the trend in the red circles, you do a pretty hopeless job. There must be a better way of projecting climate. And thankfully we have a much better way, and that's through the use of these climate models. But the climate models need to be told what's going to happen to emissions, or what's going to happen of greenhouse gases, or what's going to happen to the concentration of greenhouse gases in order for them to tell us what's going to happen to temperature, rainfall, sea level, and so on. And so in the IPCC report, a great deal of emphasis is given to scenarios which are referred to as RCPs, or representative concentration pathways. These RCPs, each and every one, provides detailed, quantified scenarios for a range of different things, including radiative forcing, which is a technical term climate scientists use it's a measure of how hard we're hitting the climate system on the head. The larger we hit, the more forcefully we hit it, the larger the changes will be. It also provides information on the atmospheric concentrations of various gases, including carbon dioxide, nitrous oxide and methane, as well as CFCs, for the period 2006 through to 2100. And it also includes quantified information on how land use change may evolve over the coming century. Now these labels, 2.6, 4.5, they're measures of that radiative forcing in 2100. So they're measures of how hard we're going to be hitting the climate system. The larger the number, the harder we hit it. These scenarios are representative because if you look at the peer-reviewed scientific literature, there are many, many different sorts of scenarios, but these are representative of the vast majority of those scenarios. But it's important to note that these scenarios aren't necessarily exhaustive. We know, for example, that there are other scenarios in which sulfate aerosols, emissions of sulfate aerosols aren't reduced as rapidly as they are in these particular scenarios. So what happens if you then take these scenarios? I should point out that, that with these scenarios, some of them vary, as I mentioned before, with the degree to which we apply radiative forcing. They vary in their regard to the amount of CO2, for example, in the atmosphere. So for 8.5, the emissions of CO2, or the concentrations, are much, much higher than they are for RCP 2.6. That's the blue one down the bottom here. So you get a whole range of different answers, and that's because no one knows for sure what emissions are going to be doing over the coming century. And so they're all projections given a scenario. And this scenario, RCP 2.6, assumes that there are going to be that are consistent with there being stringent emissions controls. on a global basis. And in some models, in order to reach these sorts of low concentrations, you need to develop technologies that are able to actually extract greenhouse gases from the atmosphere on a massive scale. Of course, such technologies don't currently exist, so you might regard that particular scenario as a fingers crossed scenario. However, you won't find any statement like that at all in the IPCC report, because the IPCC report doesn't provide any information on which of these is more likely, and it doesn't prescribe what we should be doing. It just tries to give you the information you need to make your decisions. So what the IPCC report then goes on to say is that if you want to keep global temperature change below, let's say, 2 degrees Celsius relative to pre-industrial, then a range of things need to occur. One of the new features of this report relative to older reports is that it highlights that primarily the future warming that we're going to experience is driven by the total amount of carbon dioxide emitted if you add it up all the way back to the industrial, say, 1750, 1760. So it's not the emissions in a particular year, either past or future, it's the accumulation over that whole period. And as a rough estimate, it seems as if you want to keep global temperature change below 2 degrees Celsius, then you can't emit, or we can't emit, more than 1,000 gigatons of carbon. Of course, the situation is not quite as simple as that, because this simple formula doesn't take into account some of the other greenhouse gases. So this number could be as low as 800 gigatons of carbon. And you think, well, what's a gigaton? How does that relate to what we've already done? Well, since the Industrial Revolution, we've already emitted approximately 531 gigatons of carbon. So in other words, more than half. And this doesn't include the 2012, 2013, nor does it, and the other important point to note is that currently our emissions are around about 10 gigatons of carbon per year, but that rate of emission is increasing, around about 3% per year. So you can imagine that if, taking all of those things into account, if we assume that we've been given a budget of 1,000 gigatons of carbon, say, then we would exhaust that budget within a few decades. So in order, if we actually did exhaust it in terms of emissions, we would actually need to rely upon these massive new technologies. And of course, they would have to be safe and effective. But as I said, such technologies have yet to be developed. And the other important point to note about these budgets is that they don't incorporate other factors which could be very important. One, for example, is if there was a further permafrost thaw. Permafrost is frozen soils, primarily in the Arctic, and in those frozen soils locked up a lot of greenhouse gases, methane, carbon dioxide. There's already been some thawing of that permafrost, and more thawing is expected. But what we don't know is how much greenhouse gas is going to be emitted by that continued thawing. It may be as little as 50 gigatons of carbon over the century, or maybe it'll be 250 gigatons of carbon or more. And so it's important to keep those sorts of issues in mind when you look at a plot like this, because that plot doesn't incorporate that kind of possibility. Now, those amounts, that budget of 1,000 gigatons of carbon, that's if you want to keep the likelihood of temperature change of 2 degrees Celsius below 2 degrees Celsius likely. You want to make it likely. Suppose you want to make it very likely, or suppose you want to make it extremely likely, then the budget will be much less, much less. Now, of course, not only is temperature going to increase, there will be a whole host of associated changes, and we will see, for example, further increases in sea level at rates that will surpass what we've already observed. And again, crucially, we will see more rapid sea level rise under this RCP 8.5 scenario than we would under the RCP 2.6. But even under that RCP 2.6 scenario, we see further sea level rise. And it's important to remember before we were talking about how through increasing the concentration of greenhouse gases, we've really been banging the climate system on the head. Well, the climate system takes a while to respond to the forcing, to the hitting that we've already given it. It doesn't come to a steady state overnight. It takes centuries and centuries. And so even if we were able to magically go back to the year 2000, for example, freeze concentrations at that level, there would still be further warming and there would still be substantial further sea level rise, not just this century, but for centuries beyond. Now, we've also been receiving two very important services, if you like, from the ocean. And those services are that the ocean has been absorbing a significant fraction of the carbon dioxide that we've been emitting. Now and it also has been absorbing a significant fraction, a very large fraction of the heat. So they're two very useful things. But unfortunately, those services, as Steve Rintoul was saying the other day, come at an extreme cost. One is from the heat, it's a contribution to sea level rise. The other, from absorbing carbon dioxide, is ocean acidification. Some of you, we're obviously all aware that liquids can be either acidic, basic or neutral, and the ocean is basic, but it's becoming less basic, and this has been given because it's absorbing carbon dioxide, and that process has been termed ocean acidification. So the sort of evidence that we've just looked at, and much more evidence, led the IPCC authors to the following conclusions. First, that atmospheric concentrations of carbon dioxide, and should I also add nitrous oxide and methane, are unprecedented in the 800,000 year record. Warming of the climate system is unequivocal, and human influence on climate is clear. Global mean sea level will continue to rise during the 21st century, and warming through some of the processes that we talked about, through this, through the thawing, the permafrost thawing, for example, will potentially lead to further increases in carbon dioxide release and further warming. A vicious cycle, if you like. And finally, that substantial and sustained reductions in global emissions of greenhouse gases are required, if that's what the world chooses to do, to limit warming to, for example, less than 2 degrees Celsius relative to what we had prior to the industrial era. Thank you.